We are discussing about solubility and also factors affecting solubility and also Henry's law in order to discuss the effect of pressure on the solubility of gas in liquid. So first of all, we discuss about solubility. So you know solubility is actually can be defined as the number of moles of solute which saturate, or we can define it is as the number of grams of solute which saturate 100 gram of solvent. Clear? Or we can define solubility as number of moles of solute which can saturate the volume of solvent in liter. What? Saturate. Clear? So the solubility can be defined as the number of moles of solute which can saturate the 1 liter or 1 dm cube of solvent. Clear? Saturated. Clear? Suppose we can explain it as, for example, this is the number of moles of solute. So when we dissolve it in 1 liter of solvent, so the number of moles of solute which saturate the volume of the 1 liter of solvent, the number of moles of solute which saturate 1 liter of solvent. Clear? So number of moles of solute which make a solution saturated when we use 1 liter of solvent. Clear? So, or in the other form, the number of grams of solute which saturate 100 gram of solvent. Clear? So we can define solubility as number of moles of solute which saturate or which make a saturated solution of 1 liter of solvent, or number of moles of solute, or in other words, number of grams of solute which make a saturated solution of 100 grams of solvent. Clear? So solubility you know depends upon so many factors. Number 1, nature. Here the word nature means is this molecule is polar or non-polar, or I can write it as ionic. Clear? So the solubility of any solute in a solvent depends upon nature of both. Clear? If both have here, for example, these two cases, if accept this, if the solute and solvent are non-polar, then they can dissolve each other. Then the solute of non-polar can be dissolved in, for example, if this is a solvent, if here benzene C6H6 is present, or if here toluene is present, and if here, for example, a long chain of alkane is present, so this solvent can dissolve what? If here ether is present, so this solvent can dissolve so many non-polar substances, non-polar solute. For example what? CCl4. Clear? So CCl4 can be dissolved if here benzene, toluene, alkane, long chain alkane or ether is present. Clear? So it means that the solubility of solute in solvent depends upon the nature. Here the word nature means have these solute and solvent have same nature. If both have same nature, then their solubility will be high. Clear? So here, if the solute is nonpolar and solvent is also nonpolar, then the solubility will be maximum. And so many grams of solute will be soluble in 100 grams of solvent, or so many moles of solute will be soluble in liter of the solvent. Clear? So if they have different nature, if they have, for example, if this is water, this is H2O, and we dissolve here a carboxylic acid, long chain carboxylic acid, or for example we dissolve here oil. Clear? Oil, so the solubility is very minimum, negligible. Clear? Because they have different nature. Here in carboxylic acid, I know their head is polar, and there will be some solubility, but they have, here we will study in detail. Here, for example, the nonpolar is clear. Okay, so if they have, for example, nonpolar is clear. Okay, so we are going to discuss if here is H2O, which is polar, and when we dissolve here such substance which have different nature. So the first one is that if the solute and solvent have same nature, means the solute is nonpolar, solvent is also nonpolar, then the solubility will be maximum. More solute, more quantity of solute in grams or in moles will be soluble in the quantity of the solvent in grams or in moles. Clear? Okay, so if they have different nature, for example, this is H2O, and if I want to dissolve here what? If I want to dissolve here CCl4, this CCl4 cannot be dissolved here up to some extent. Clear? So if I dissolve here carboxylic acid, what? Or if I dissolve here ester, such as or for example that, or waxes or oil. Clear? So there are some oil which can be soluble up to some extent, but their solubility is very minimum or negligible because they have different nature. Clear? This is most polar, while here this is non-polar region and this is also non-polar region. So due to this non-polar chain, their solubility is also minimized. Clear? So for the first, if both solute and solvent are non-polar, their solubility will be maximum. Here, if the solute and solvent are polar, then their solubility will be maximum. For example, this is a H2O. Clear? So when we dissolve here, dissolve what? Alcohol. Clear? For example, glycerol, and for example so many other low molecule of carboxylic acid, low molecule of carboxylic acids. Clear? So many other is also present. So these molecule are ionic substance. For example, sodium chloride, sodium hydroxide, these can easily be hydrolyzed or dissolved. Clear? So if the solute and solvent have same nature, means both are polar or both are non-polar, then their solubility will be maximum. If they have different nature, then their solubility will be maximum or minimum. Clear? If they have same nature, solubility will be maximum. If they have different nature, means one polar and other non-polar, either solute polar, solvent non-polar, either solvent polar, solute non-polar, then there will be low solubility. Clear? So the first one, nature. The second one is temperature. Second one is temperature. Temperature. Clear? So there are two types of reaction on the base of solubility. One type is endothermic reactions, and the other one is exothermic reactions. Clear? So if this is a solvent, and this is a solute. So if the reaction to form A plus B, clear? Suppose this is a two molecules, this is one molecule and this is also another molecule. Clear? So if these are two molecule and there is a van der Waals forces. Clear? Or for example, these are two molecule and there is van der Waals forces. Clear? So when we want to dissolve it here, clear? So what will happen if the reaction of AA to form A plus A is endothermic, then upon heating this these molecules, clear? Upon heating this molecule will favor the solubility to form A and A. And if AA bond breaking, AA attraction breaking, or if the solubility of AA to form A plus A in that solvent is exothermic, upon heating this substance, its solubility will be decreased. So a substance who are exothermic in nature during solubility. So when we heat this substance, so if this is an exothermic reaction, so upon heating their solubility will be decreased. And if any substance upon dissolving, upon solubility absorb heat, then when we heat it, when we give heat to this substance, then their solubility will be increases. Clear? So for endothermic reaction, endothermic substance favor heating, and exothermic substance not favor heating. Clear? So endothermic substance increases their solubility upon heating, while exothermic substance decrease its solubility upon heating. Clear? Okay. The third one is most important, which is pressure. That is pressure. Third one is pressure. So if these are two container, this is a solvent 1 and this is a solvent 2. Clear? Suppose 1 and 2. If I dissolve a solid substance here, then there will be no pressure, there will be no role of pressure increasing or decreasing here. If I dissolve liquid solute in this liquid, then there will be no role of pressure. So the pressure doesn't play any role in solubility of solute in solid form in liquid, or in solubility of liquid solute in solvent. Clear? So here there is no role of pressure by increasing or decreasing when we dissolve solid in liquid or liquid in liquid. But when we dissolve gas in liquid, there will be just like the pressure play a role like a backbone. Clear? So here upon increasing pressure, solubility of the gas in this liquid increases. If the pressure increases, if the applying pressure increases, solubility increases. Clear? If the applying pressure increases, solubility increases. But here the applying pressure of what? If the applying pressure of gas increases, solubility of this gas increases. Clear? So, for example, if this is a container, if this is one container and this is a second container, clear? So these two are closed. This is a liquid and this is a liquid. If there are suppose 10 moles of gas, and here there are 1 mole of this gas. Clear? This is a liquid 1 or this is a liquid 2. These two liquid are same, suppose H2O and H2O. Clear? This is a gas and this is a gas in the vacuum. Clear? In the empty space. Okay. So upon applying pressure means, or if there are more number of gas, the pressure of this gas will also be more. So these gas molecule will exert pressure on the liquid surface, and as a result they will dissolve here in this liquid. Here there is very small number of molecules on the surface of liquid, so the collision of gas molecule to the surface of liquid is very least. So as a result, the very low number of molecule of this gas will dissolve or will be soluble in the liquid. Means if the number of gas molecules on the surface of water molecule increases, means its pressure increases on the surface of water. So if the pressure of the gas of any gas increases on the surface of water, means its solubility increases. So in order to explain the solubility of gas in the liquid, we use Henry's law. So according to Henry, he said that the partial pressure, suppose for example, this is a closed container and this is a liquid where gas is dissolved. This is a liquid where gas is dissolved, and there is a vapors of this gas. Okay, this is a liquid in which gas is dissolved, and these are the vapors of this gas. Okay, so according to him, the partial pressure, okay, here the partial pressure of the gas above the liquid surface, the partial pressure of the gas above the liquid surface is directly proportional to mole fraction of this gas. For example, A. Clear? Of Pa, suppose the partial pressure of the gas above the liquid surface is directly proportional to the mole fraction. So if the mole fraction in any liquid of any gas increases, it means its more vapors of this gas will be formed. Clear? Because you know that the partial vapor pressure of any substance in a solution form is equal to P naught A multiplied by mole fraction of A. Here it means that if the mole fraction of anything increases here in a solution form, it means that its vapor pressure, for example, here the gas mole fraction is that. Clear? And here the pressure is that. So if we increase the mole fraction of gas in of any molecule of any volatile substance here, if we increase the concentration of any volatile substance in this solution, then its vapor pressure will be increased, because more the number of molecule of this volatile substance in this solution, more will be its vapors. If more will be its vapors, more will be its vapor pressure. Clear? So it means that the pressure, if this is a solution in which we have dissolved a volatile substance, or in which we have dissolved a gas here, so if we have dissolved gas in this liquid, so above the liquid there will be a gas particle of this gas to which we have dissolved. Clear? So if we have dissolved a large number of gas in this solution, in this empty space there will be more vapors of this gas or more molecule of this gas. Clear? So according to Henry's, the partial vapor pressure of the gas above the liquid surface is directly related to mole fraction of gas in liquid or in solvent. Again, according to Henry's, the partial vapor pressure of the gas upon liquid surface is directly related to mole fraction of the gas which is present in this liquid. So if we have dissolved a large number of molecules, a large number of moles of this gas in this solution, then there will be more vapors. If the mole fraction of the gas is less here, then there will be low number of molecule here. Okay, so here we put the partial pressure, we can write it simply. The partial pressure here, the partial pressure or the partial vapor pressure of a gas, the partial vapor pressure of a gas above the liquid surface is equal to kh x. X is moles gas in liquid. Clear? Mole fraction of gas in liquid. Here P is pressure, partial vapor pressure. Kh is the Henry's constant. This is a Henry's constant. Clear? And this is the mole fraction of the gas in solvent. Clear? We are going to discuss it in detail. So now, what is kh? What is the unit of kh? So you know mole fraction have no unit. Mole fraction have no unit. We know that. So Pa can also be rewritten as kh and xa. Clear? So I want to remove this x. Clear? This a. Clear? So here x means mole fraction of gas in liquid. Clear? Okay. So what is the kh? So you know that kh is equal to Pa divided by x. Okay, here I will discuss it also. So first of all, what will be the unit of kh? What will be the unit of kh? So you know that here the Pa is equal to kh into x. Here the x have no unit. So if pressure unit is Pascal, then kh unit will be also Pascal. If this is atmosphere, its unit will be also atmosphere, because it have no unit. If I remove x mole fraction from that, So P Pascal or the partial vapor pressure of solute or on the of gas above the liquid surface will be equal to kh, means these both have same units. Clear? So again here kh and mole fraction have inverse relation. Here kh and x have inverse relation. For example, if kh increases, mole fraction will be decreases of gas in liquid. If kh increases, mole fraction of gas in liquid will be decreases, means another quantity. For example, temperature. I am also discussing temperature here. If temperature increases, we know that if temperature increases, the solubility of gas in liquid decreases. I am explaining the reason. If temperature increases, the mole fraction, or simply if temperature increases, the kh increases, means mole fraction of a gas in liquid decreases. Okay. So for example, this is a container and this is also another container. Here the water is cold and this is hot. Here the percentage of oxygen is 21%. Here is also 21%. So the question is that in which water the concentration of water will be maximum. Here the concentration of water will be maximum because here the temperature is low, where here temperature is high. Here the kh is low, here the kh is high. Clear? Here the mole fraction, means here the mole fraction is high, here the mole fraction of gas in liquid is what? Low. Clear? Because they are inverse. Okay. So that's why the aquatic animals want to live in the lower surface of the ponds, because here the temperature is very low and the solubility of gas is very high. Clear? Okay. So according to Henry, the partial vapor pressure above the liquid surface is directly related to mole fraction of the gas in liquid. So we put here Henry's constant, and Henry's constant have same unit as pressure. Clear? And Henry's constant have inverse relation with the mole fraction of the gas in liquid. Clear? If temperature increases, kh increases, a mole fraction or the concentration of gas in liquid also decreases. If temperature increases, kh increases, the mole fraction or the concentration of the gas in liquid decreases. Okay, this term are clear. So now I want to discuss the graph between the, you know that P is equal to kh into x. So P is at y. Clear? K is the slope, it is a slope, and this is a mole fraction which will be at x-axis. So this is a pressure, partial vapor pressure. This is a partial vapor pressure of gas above the liquid surface, and this is a mole fraction of a gas in liquid. This is a mole fraction of gas in liquid. Okay, so you know that the partial vapor pressure have direct relation to mole fraction of the gas. So it means there is such type of graph. So if anyone ask about the slope, so you know that this is a slope and Ka is equal to P by x. X means mole fraction. So here will be the slope theta, and slope is equal to tangent theta, which is equal to Ka, and which is equal to P by x. Okay, so we are going ahead. So now we are discussing some other angles some other angles of numericals. Clear? So okay, so you know that this is our basic formula. Mole fraction, the partial vapor pressure of the liquid above the partial vapor pressure of a gas above the liquid surface is directly related to Henry's constant and to mole fraction of solute in a gas in a liquid. So the examiner can ask about, he can the x, sometime x is given, x mole fraction of a gas in liquid is given, and kh is also given. They ask about the partial pressure. Clear? So they ask about the partial pressure of the liquid above the gas. This is a one type of numerical problems. Other type of numerical problems, sometime the question is that partial pressure is given, partial pressure of a gas above the liquid surface is given, and kh is also given, and they can ask about mole fraction. This is a second type of question. Clear? Okay. The third type of question is that sometime partial vapor pressure of gas on the liquid surface is also given. Clear? And kh of solute is also given. Here you know that mole fraction of gas in liquid, here moles of solvent is given. Clear? The question is moles of solute, to which we will find. Clear? So what will be its structure? Clear? Partial vapor pressure is equal to kh multiplied by moles of gas divided by moles of what? Mole fraction. It is a mole fraction. Moles of what? Moles of gas plus moles of solvent. Clear? Okay. So sometime the examiner can ask a question about molar mass or mass. For example, P is equal to kh multiplied by mass of gas divided by molar mass of gas divided by mass of gas divided by molar mass of gas plus mass of solute divided by molar mass of solute. Okay, so these are some angles about which examiner can ask a question. So other type of question, numerical question, in which the students cannot differentiate is that sometime. So my first question is that if kh increases, solubility decreases. If kh increases, solubility decreases. It means if kh increases, solubility decreases, mole fraction decreases, attraction between solute and solvent decreases, the nature of solute and solvent it is also different. Okay, so if temperature increases, kh also increases, mole fraction decreases, solubility of gas in liquid is also decreases. Okay, so sometime examiner can ask a question such that, for example, this is an air. Clear? And this is a pond of water. Clear? So sometime they say that if the pressure of air pressure of air is approximately 10 atm, for example, or 1 atm. Pressure of air is equal to 10 atm. And also, for example, we know that pressure, partial vapor pressure is equal to kh multiplied by mole fraction. Mole fraction, for example, we can write it as, it is a kh. Okay, so the examiner can ask the question, if the pressure above the liquid is of air is 10 atmosphere, if the pressure of air above the liquid surface is 10 atmosphere, for example, and mole fraction, find mole fraction of x of gas in liquid. Find mole fraction of gas in liquid if kh is also given. The question is that what will be the pressure P, what will be the partial vapor pressure if mole fraction is that, if mole fraction is that, suppose 1 2 3 4 5, suppose 0.8, clear, or 0.9, 0.5, and kh is also given 1.3 10 raised to the power something. So he asked the question about what? The question about the partial vapor pressure of the liquid, of the gas above the liquid surface. So you know that this is a total pressure, P total. This is a total pressure. Okay, this is a total pressure, and you know that in air, if this is 100 molecule of air, here approximately 80% molecules of nitrogen, and 21% but 20% of O2. Okay, so how we will solve, how we will find the partial pressure for that. Okay, so now this is a mole fraction, we will put the value here. The kh is also given, clear, and we will find the value of Pa. Okay, is there some other way to find the partial vapor pressure? So the other way is that the partial vapor pressure, this is the one way on the basis of which you can find the Pa. The question is that mole fraction is that, Ka is that, find P. So put the value in this equation and find P. Another, you know, by using Dalton law, if this is a liquid, clear, this is a liquid, and this is a gas whose pressure is 10 atmosphere. So how you will find the partial pressure of a gas? So the partial pressure of a gas is equal to total pressure multiplied by mole fraction of this gas. Clear? On the basis of this way, you can find the partial vapor pressure for any substance. So I hope that you have learned something more. So if you want to study such type of beneficial lectures, subscribe the channel and also click on all notification bell icon in order to get such type of beneficial lecture. So at the end, goodbye.